Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing a crash course on the topic of forces, density, and pressure for Cambridge AS Physics 9702. So AS Physics is your first year of A-level physics, and the topic of forces, density, and pressure attempts to introduce us to the turning effects of forces, the definition of mass density, and also the definition of pressure. And we go into a little bit of detail on hydrostatic pressure, that is liquid pressure. But this topic is basically an introduction to things like density and pressure, which we'll meet again later on in A-level physics. So this crash course, like always, is just going to give you a recap of just the most important things that you need to know in the topic. But I may omit some things that are equally important. So the onus is on you to make sure that you read through the topic carefully, you understand it, and you are able to solve problems as well. But I have solved paper 1 and paper 2 questions on this topic, so make sure you check those videos out. If you are done with the concepts and you want to go into the problem solving. But this crash course does require us to start off with a little bit of a recap of what is a force. And I'm not going to go into the full definition of what a force is, but basically, and very poorly, this is very un-physics teacher-like of me, but I'm going to say that a force is a push or a pull, which kind of does the job for us for now. It's something that when applied to an object and is unhindered or unopposed will provide that object with an acceleration. So if the object can feel the force and there is no opposing force, then the object will have an acceleration due to this force. So that's our definition of force. A push or a pull, I push an object, it moves in the direction of the push. If I pull an object, it moves in the direction of that pull. But this will come in handy later on, and you'll see why I'm describing a force, because we need forces to describe what a turning effect of a force will be. But before we even get there, we need to describe something that, some of you may have seen this before, some of you may be seeing this for the first time, some of you may have heard of this phrase, but not have an idea of what it actually means physically. And that's center of gravity. Now, what is the center of gravity? The center of gravity is the point on an object where its weight is considered to act. So actually, me being too lazy to write this out means I'm just going to type this, but it's the point on an object where the weight can be considered to act. And I'll explain what this means. So what does this mean? A point on an object where the weight can be considered to act. Well, the weight is a force. And up until now, we've been assuming that forces act on a point. So here's a point, and there's a force acting downward. And if this force is equal to the weight of the object, if this is only due to gravity, then this force W is the mass of the object times the acceleration of free fall, little g, which is 9.81 meters per square second. Well, that's all well and good, but where in nature do you actually get an object that just occupies a point in space but has a mass? It's very rare that you have an object of significant enough mass that it has a weight, but only exists at a point. Objects with mass usually occupy regions in space. They're large objects, and hence they feel the effects of gravity. So what I will do is I'll show you what this actually means. And what I'm trying to say is that we need to take a 2-dimensional, 3-dimensional object and replace the object by a point in space so that we can make the calculations easier to do. That's all basically what we need to do. So the center of gravity is taking a massive object and reducing it to a point and assuming that the weight acts only at that point. That makes our mathematics a lot easier. So let's take a uniform rod. I'm using the word uniform loosely, but what I mean is uniform rod, meaning the mass is distributed equally throughout the rod. So at every point of the rod, there's the equal spacing of mass. So I'm going to draw it as basically a cylinder, and I'm going to align the cylinder. Believe me, this is a cylinder. It's obviously a lot easier to draw on pen and paper, but I'm going to align the cylinder horizontally, meaning that the core of the cylinder, the central axis, lies on the horizontal or x-axis. We'll call it the x-axis. The length of the cylinder, like I said, is 0, a. It's a, so it lies, the one end of the cylinder lies at the point x is equal to 0, the other end at x is equal to a. And we know that if it's uniform, if its mass is distributed equally throughout this cylinder, then obviously its weight will act to the center. Kind of makes sense, right? Because the mass on the left and the mass on the right completely balance, so the center of mass or the center of gravity would be the central point. Okay, and that's because the mass is evenly distributed. So for calculation's sake, what I would do is I would replace this entire cylinder with just a point in space, and that point will be halfway between 0 and a. So this force, the weight, acts at only one point at x is equal to a over 2. Now, yes, this is a simplification, but it's a simplification that we are going to use for A-level physics. Obviously, when you're doing things like engineering and so on, you're going to have to be a lot more careful about just using centers of mass. You can actually talk about using calculus to determine the effect of forces on objects, but we're just going to assume that objects have a center of mass at their geometric center. But what about if I have a rod that was made from two different materials? So instead of being made from one material, like the first rod, for example, could be made from simply copper, and copper has a constant density. But then I have a rod that's made from two metals. Maybe half of it, or an eighth of the rod, is made from copper, and the other 7/8 made from steel, whatever. So let's say we have a non-uniform rod now, which looks identical, but obviously the way that the mass is distributed is not even. And I do the same thing to this rod. I lay it horizontally so that its axis, its central axis, is again on the x-axis. So I'm not drawing these to scale at all, but if it has a length a, then its one end lies at x is equal to 0, the other end lies at x is equal to a. But now let's assume that the weight, the center of gravity rather, is somewhere towards the left end of the rod, meaning the left end of the rod is much heavier, and the right-hand side after this point is much lighter. So the center of mass, if I were to balance it on my finger, it would balance at this point where W is acting. And this center of mass is not at the center because the center of gravity, rather, is not at the center of the geometric center of the object, because the mass is unevenly distributed. I'm not really going to show how to calculate centers of mass, but just so you know where it is for mathematical purposes when solving problems with the turning effects of forces. So here, W acts at some point x that is a lot less than a over 2. A over 2 would be the center of the rod, and W is not acting to that point. It's acting to a point much to the left of that. So the center of mass would be weird, but this object would balance if I put my finger at the point where W is acting, and that would be the center of gravity. That would be the point at which the rod would balance. So this is basically what the center of gravity tells us. It just tells us the point at which the force is acting. This is important because we need to know where the force is acting in order to do calculations with the force. Because if I know where the force is acting, then I can use the force and a distance associated with that force from a certain point, which we'll see later on. But that's basically the center of gravity. So very important just to understand the concept. You don't need to know how to calculate it, but if you do, that's great. The next thing I want to talk about is the moment of a force. Remember, this again is a crash course, so we're going to be moving relatively fast through the concepts, and you need to make sure that you are happy with all of these concepts. Again, if I've left out anything, please let me know, but I think there's more than enough just as a recap, as a basic revision of the topic. So what is a moment of a force? Well, there's a question I want to ask, which is, we know how a force moves something. Like, if I push something, it moves away from me. If I pull something, it moves toward me. But how does a force turn something? That's the question that we need to ask when we're thinking of the moment of a force. And the answer to this, how a force will turn something, is the moment. And the moment of a force is a physical quantity, and it's the quantity that gives us the turning effect of the force. So the turning effect of the force is called a moment, also known as a torque. We use it slightly differently in A-level physics, but the moment of a force and the torque is essentially the same thing. Now, how do we calculate the moment of a force? Well, the moment of a force, and again, you may know this equation, is the force itself multiplied by the perpendicular distance that the force acts to the pivot. So I'm just going to say perpendicular distance to pivot. Ooh, the pivot, what is the pivot? Well, I'm going to describe that when I draw the diagram, but a pivot is basically a point around which something turns. When something turns, it must turn around something. And that point around which it turns is called the pivot. Pivot is basically the point that's remaining fixed whilst the rest of the object is moving around that point. So this is why we needed to figure out what center of gravity was, because we need to find the distance of the force to the pivot. And if that force happens to be weight, then I need to know where the weight's acting in order to know its distance to the pivot. Hence, I needed to figure out what center of gravity was. So let's draw an example. Let me use a uniform rod. And if I don't say anything about these rods, just assume them to be uniform. If I forget to mention anything about these rods, just assume that they're all uniform. And actually, let's write it down. Uniform rod. Here's a uniform rod. It has a length L. I mean, from any material, doesn't really matter. And, oh, by the way, if the moment of a force is the force multiplied by the perpendicular distance of the force to the pivot, then the unit of measurement, which I represent usually with a square brackets, the unit of measurement for the moment of a force is a Newton meter. Force is measured in newtons, distance is measured in meters, so simply Newton meters. We don't have a, well, at least for now, we don't have a derived unit for moment. And so I'm again going to place this rod like I've done before along the x-axis. The one end of the rod is at x is equal to 0, the other end is at x is equal to L. And I'm also going to add something to this rod. I'm going to hang a mass M, and this mass is going to have its own weight. I'm going to call it W, and this W is equal to mg. And this mass will place it at a point A along the horizontal axis. Now we also know that this rod has a weight, and since the rod is uniform, the weight of the rod acts through its center. Hence, I had to know centers of gravity. Uniform rod means the weight acts through the center. And obviously the weight acts at a point of half the length, L over 2. And this is my pivot. I was going to tell you what a pivot was. The pivot is the fixed point around which this object can rotate. So think about what's happening. I have the weight of the rod pulling it down. I have a mass attached to the other end. So if I have my pivot, maybe some hinge on a wall, what's going to happen is there's going to be a clockwise rotation because the right end is not fixed. It can move. And since there are two forces here that are going to help this rotation be clockwise, those two forces contribute to the moment of this rod about the pivot at x is equal to 0. So that's what a moment basically is. So if I were to calculate this moment, and there's only one moment here, it's the clockwise moment rather. We can have moments being clockwise and anti-clockwise, just like we can have forces being positive or negative, left or right. Moments can be clockwise or anti-clockwise. And so the moment is the weight of the rod multiplied by the perpendicular distance that this force, the weight of the rod, acts to the pivot. Well, that's that distance from 0 to L over 2 because the weight acts at x is equal to L over 2. Why am I saying perpendicular distance? Because the distance is along the length of the rod and the force is perpendicular, it's downwards. So there's a 90-degree angle between the two. But there's another moment that also contributes to the clockwise motion, and that's the weight of the mass that is attached to the rod. And it acts at a distance a. So its moment will be the force that it applies, mg, times a. And so that's the total moment. It is where the force is perpendicular to the distance, or the displacement rather, I should say, from the pivot. Aha. So this case was quite simple because the forces were down and the distance was obviously measured along the rod, which is horizontal. Horizontal and vertical means perpendicular, so the moment is just force times distance. Force times distance, we add the two and we get the total moment, or what we get is the net moment. But what happens if one of these forces acts at some weird angle? What happens if they don't act at in the direction that that makes it convenient for them to be perpendicular? What if they are inconvenient? So let's change it up slightly. So let's say that the forces are acting at some angle, and repeat the process. So I'm going to use a rod again. Yeah, I'm trying to use the simplest examples, but this is a rod, and we're going to fix the rod again at the left end at x is equal to 0. And at some distance d, I'm going to have a force acting on the rod down and to the right, rather than simply just down. And so what actually happens here is, now I'm going to remove the x, but what happens is I have a force F pulling down on the rod, and this force is going to have a rightward component, Fx, but at the same time it's going to have a downward component, Fy. And then there's an angle theta here we can call between Fy and F. Now, the component that is perpendicular to the rod is the one that actually causes the rod to turn. So there'll still be a clockwise rotation, but the moment here, due to this force, whatever's causing this force, it could be a tension in a string, etc., is only the y component of the force multiplied by the distance d, the perpendicular distance d. So Fy and d are perpendicular, and so we can use those two to find the moment. But if I do a little bit of mathematic, this turns out to be F cosine theta times the distance d. So when the force is at an angle, you have to find the component of the force that is perpendicular to the rod, and then find that distance to the pivot point. And so there's going to be a use of sines or cosines when you're using components of a force rather than the force itself, because the force is at some angle, which is a common type of problem. You will have seen these in your textbook, in your exam, past exam questions, and so on. Okay, so that's how we deal with forces at an angle and find the moments of those forces. Okay, so it's novel, but it's not difficult. Where it does get difficult is when we apply many forces all at the same time and try to balance them appropriately. Now, the thing that follows on from a moment of a force is a couple. So what is a couple? Well, in physics, a couple is a set of two forces that have equal magnitude. Well, that's easy, isn't it? Well, it doesn't really end there. Any two forces can have equal magnitude, but if they act in the same direction, then they're not a couple. So we have another criteria that says that a couple is a set of forces that must act in opposite directions. So they must have equal magnitude, they must act in opposite directions, and they must have different lines of action. So they shouldn't act along the same line in opposite directions, because that really wouldn't make anything happen. They would just cancel each other out. So what does this mean? Well, practically what this means is if I draw this amazing circle freehand without any assistance at all, what I find is that if I have this circular object, it could be the side-on or the cross-sectional view of the handle of a screwdriver, for example, and I apply a force to the top end of the handle to the right, and the force has a magnitude F, but at the same time I apply an equal and opposite force to the bottom end of the handle, the same magnitude F on the opposite direction and a different line of action, then I have a couple. And we assume that this diameter, the diameter of this handle, cross-sectional diameter, is D. We say the torque of this couple. Torque is, like I said, similar to moment. We sometimes give it the symbol, the Greek letter tau, the Greek letter T. But we don't always do that, so you can simply write torque. The torque of a couple is equal to the magnitude of one of the forces times the perpendicular separation between the forces. But torque, just like moment, is another word for turning effect. If I increase the force, I increase the turning effect, obviously. But also if I increase the distance, then I increase the turning effect. So I have a much wider diameter screwdriver, then I can increase the turning effect. But also it has to be wide enough that it's comfortable to use and not too wide that it doesn't fit in your hand. So you have to balance out somewhere practicality with the most amount of torque that you can get. And so this is called a couple. Two forces, opposite directions, equal in magnitude and separated by some distance d. But again, it's perpendicular distance between the forces. So force times perpendicular distance. Again, if the force acts at some angle, you need to find the component that is perpendicular to the line that is joining the two forces. Okay. And this is important. All of these things are important because there's a thing called the principle of moments, which we have to know. Now, we spoke about equilibrium earlier, and we said, well, for static equilibrium, we have to make sure that an object has no net force acting on it, meaning all the forces on the object must be balanced. But if I look at this object, all the forces in it are balanced, and it's not translating, but it's going to rotate. In fact, it's going to rotate in a clockwise direction because I'm pulling to the right at the top and pulling to the left at the bottom. This circle is going to rotate in a clockwise direction. So it's still moving. It's just not translating. It's rotating. So if we want to stop the object from rotating, the principle of moments says that for rotational equilibrium, to make sure there's no net torque on an object, no net moment on an object, for an object to be in rotational equilibrium, the sum of all the clockwise moments on that object must equal the sum of all the anti-clockwise moments. I'm not writing it in full, but you know what I mean. When you open your textbook, you'll see this there. The sum of all the clockwise moments must equal the sum of the anti-clockwise moments, provided that these moments are taken about the same pivot, about some point. And so that's the principle of moments. So if we want an object to be truly in equilibrium, there must be no net force on the object and no net moment. If there's a net force, the object will translate. If there's a net moment, the object will rotate. So if we remove both net force and net torque, an object is truly in equilibrium. Because you can have an object that's rotating but not moving left or right, like we would in this example that I've done before. So that's the principle of moments. Read it, be able to write it in words. Please don't write it the way I have. I'm just simplifying out of nothing but pure laziness. But that's the principle of moments. So moving away from the turning effects of forces, we need to talk about the second half of this topic, if you want to call it that. And that's density and pressure. So we need to describe or define what density is, and then define what pressure is, and then do a little bit of examples of both. So density, we give it the symbol, well, something like that. I can't draw it exactly as it should be, but this is not a P. It's actually a Greek letter called rho. It's actually an R, not a P. It looks like a P, but it's actually slanted to one side. So this is the Greek letter rho, and density, or mass density, as we sometimes call it, is the mass per unit volume of an object. It's the mass of the object divided by its total volume. How many kgs am I getting for every square meter of the substance? And what this means is that the unit of measurement for density is kg per cubic meter. As I would expect, most of you would have seen density at some point. Maybe you gave it a different symbol, but we'll use rho to define density, or as the symbol for density. The other thing we need to use is pressure, or define is pressure. Now notice how my P is upright, but my rho is slanted. So make sure that these two look different, especially if they're in one equation with each other. The definition of pressure, which I'm also sure you would have seen at some point, and should be fairly comfortable with, is a force per unit area. Now, what I should mention is that density is a scalar, and pressure is force per unit area. What could that possibly be? We'll get back to that. But the unit of measurement for pressure, if the pressure is a force per unit area, is then measured in units of Newton per square meter, which we give the derived unit of the Pascal. And guess what? Yes, it's a force per unit area, but it's also a scalar value. Weirdly enough, pressure doesn't have a direction. Pressure can act in all directions, but doesn't have a specific direction. It's just a scalar quantity. It can have a size, but it can't have a physical direction. Force can have a direction. Okay, which is kind of weird, but we're actually not going to talk about why that is for now. The pressure is a scalar just like density. But what about if I take it one step further? So why are we learning about density and pressure? It's because we really want to talk about the pressure in a liquid, which is sometimes called hydrostatic pressure, or simply liquid pressure. Liquid pressure is a lot easier of a way to call it. So let's assume, now let's actually test what a pressure looks like. Let's assume that I have maybe a piece of paper or some other material, maybe some plastic, and it has a surface area A, and this is only one face. So one face of this object is placed under some water. Let's see if I can draw water. Yeah, believe it or not, it is in some container, and there's a column of water above it. And this column of water has a weight W. And this column of water also has a height of H. So the length of this water column from the top of the water surface to the face of the object is H. So what we have is that the pressure exerted on the face of this object, on the face of the surface area A, is equal to the force per unit area, the weight of the water divided by the area over which that weight is distributed. And this is m times g over A. Let's assume the mass of water is m, and g is the free fall acceleration. But wait a minute, we can write this as rho times v times g over A. Remember that the mass of an object is also can be written as its density times its volume, because what did we say? We said density is mass over volume. So if I took the v across, I get that mass is density times volume. So that's another way of writing mass. So I get rid of the mass of the water. The density of water is a constant. We know it to be 1000 kg per cubic meter. If I multiply the density by the volume by the constant g and divide it by the area, I get the pressure. But wait a minute, this is a column of water. You can think of this as a box of water, essentially. And volume divided by area is simply going to give me the height. So P is equal to rho g h. Why? Because the volume of water is the surface area times the height of the column. So the surface area multiplied by the height is going to give me the total volume occupied by the water. So the pressure, which we sometimes call hydrostatic or liquid pressure at a depth h, is rho gh, where rho is the density of the liquid. In this case, we use water, but it could be any liquid. H is the depth of the object below the top surface of the liquid. Okay, so this is very interesting. So now, what if I expose two faces of an object? What if I expose an entire three-dimensional object to this water? So I'm going to draw again the face, one face of an object. Now this object is going to be three-dimensional rather than two-dimensional as we had before. It's going to be a whole cube. Well, not completely cubic, but it's going to be some parallelepiped. And yes, that is a word, you can Google it. And here's my box. I think box is a much easier word to remember. The top face of this box has a surface area A, and the bottom face of the box also has a surface area A. Even though it doesn't look like it, it's boxy enough. But I take this entire box and I again place it under water. I submerge the entire box. Okay, so now I have two surfaces, both with the same surface area, but at different depths. So the top surface is at a depth h1, and the bottom surface is at a depth h2. And now we have two faces that are perpendicular to these distances h1 and h2. But since they are at different depths, there'll be a difference in pressure, delta P, that arises between the bottom face and the top face. And delta P is P2 minus P1. And I can use the equation above, rho GH, to write this as rho GH2 minus rho GH1. Obviously, rho and G remain constant because the water is not changing density, neither is G changing value. And so I get the difference in pressure between the top and bottom surfaces of this box is rho G delta H. So if I place this three-dimensional object into the water, it actually has a greater pressure at a lower depth and a smaller pressure at a greater pressure at greater depth and lower pressure at lower depth. And so the net pressure would be actually at the bottom. The greater pressure would be at the bottom, and so the net force would actually be at the bottom, pushing the block upward. And this is the origin of the upthrust, the fact that there's a greater pressure at greater depths. This is why many objects when submerged in water will be pushed upwards since there's a net force acting upwards. And we call that force upthrust, which is the last thing we want to discuss in this video. But this is hydrostatic pressure. Now the name for it, I said liquid pressure, but I needed to write it down, hydrostatic pressure. And the word that I used earlier on that sounded like it was made up is parallel E pipette. Probably pronouncing it wrong, but anyway, you can Google it. It's actually that shape. Okay, so the last thing we want to discuss in this video is the upthrust. And again, this upthrust is very important because it generally comes up in paper 1 questions and paper 2 questions and so on. So you need to know what it is. But basically, I'm now going to, instead of using a cube and submerging a cube underwater, I'm going to take a cylinder. Again, it doesn't really matter the shape of the object. The rules still apply. I'm going to take a cylinder, a circular cylinder that is, meaning the extreme faces are circular in shape. The cross section is a circular. And the bottom and top surfaces are the same. And both surface areas are A. The top and bottom surface areas are the same. It's A. And the top surface is at a depth h1 like we had before. And the bottom surface of the cylinder is at a depth h2. And then there's some liquid surrounding the cylinder. And we'll say the cylinder has a length of L. So the total length of the cylinder is L. Okay. So the difference in pressure between the top and bottom surface is rho times G into H2 minus H1, like we said before. It's a hydrostatic pressure. But we also know that pressure is equal to force per unit area. Now, we'll come back to that expression. But remember that we said that the pressure at the bottom, since it's at a greater depth, is greater than the pressure on the top surface of this object, which means that, and again, because of the weight of water that is acting on all sides, remember pressure acts in all directions, so the pressure is being applied to the top surface, and hence there's a force on the top surface, and that force must point downward. It's pushing against the top surface of the cylinder. And from the bottom of the cylinder, there's a force pushing upward, also due to the water pressure. There's a force downward and there's a force upward. Now, since the pressure at the bottom is greater than the pressure at the top, the force that is pushing upward must be greater than the force that is pushing downward, especially because the areas are the same. So the force upward must be greater than the force downward. So what we call this net force that will arise because of the difference in the forces acting up and down is called the buoyant force or the upthrust. We can use these terms interchangeably, at least for now. The buoyant force or the upthrust, FB, sometimes called U, whatever. It is the net force, it is the force up minus the force down. And it is the difference in forces. So we calculated the difference in pressures. If we take the difference in pressures and multiply it by the constant area A, we get the difference in forces, which is rho GA times H2 minus H1. But wait a minute, if I take H2 minus H1, I get the thing that I've drawn a curly bracket next to. I get the length of the cylinder. So this becomes rho GA times the length of the cylinder L, which means that this upthrust or buoyant force is equal to rho GV. The volume here is the volume of the cylinder, its surface area times its length. But what else is this the volume of? It's not just the volume of the cylinder, it's also the volume of the water that is displaced when I put the cylinder into the water. So the volume of the cylinder is the same as the volume of the water that is displaced. Because where's the water going to go? If I put the cylinder in, the water has to move away. And so the volume of the cylinder must be the same as the volume of the water that's displaced. So the volume of the water displaced, V, and multiply that by the density of water, rho, will give me the mass of water. That's where something arises that you may have heard of, called Archimedes' principle. And so Archimedes actually found this many years ago. And basically Archimedes' principle says that the weight of the liquid, not necessarily water, it could be any liquid. I'm saying water, I'm using that word quite loosely, but what I actually mean is any liquid. The weight of the liquid displaced when I place an object in the liquid is equal to the upthrust. Weight is a force, upthrust is a force, and that's because the volume of the cylinder must equal the volume of the water displaced. And volume times density is mass. Volume times density is mass. M times G, mass times G is weight. And so the weight of the liquid that is displaced is equal to the upthrust on the object. That's interesting, because if I wanted to measure the amount of liquid displaced, or I wanted to measure the upthrust, I can simply look at the amount of water that is displaced. But also I can use this method to calculate the mass of objects by submerging them in water, or any liquid, to be fair, as long as I know the density of that liquid. Okay, so that last concept was Archimedes' principle. It's good to know what Archimedes' principle says. We don't really do any further calculations, but also it is important that you know what the upthrust looks like, and you're able to work with this when solving problems. So this was a very quick crash course on the topic of forces, density, and pressure. You need to just make sure that you understand these concepts. You need to be able to apply these concepts for objects that are submerged in water. Where does the origin of the upthrust come from? What is the moment of a force and the torque, etc.? It's not a very long topic, but it's a significant one, because all of these concepts will be used in future topics with the assumption that you know them. So you can't stop here, skip, and carry on. You need to understand and then move forward. So I hope this crash course was helpful. I hope it's helped clear up some misconceptions. I hope it's just managed to bring some sort of clarity to the topic. If it was helpful, please leave a like or a comment to tell me what could have been changed or what worked well. If you haven't subscribed to the channel, please do so now. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.